Welcome to section 2.1. In this chapter, chapter 2, we're going to be talking a lot about applications of integrals, especially as they relate to computing areas and computing volumes, which are certainly important problems, and we want to generate some techniques for computing these areas and volumes of various shapes, whether they be two-dimensional, three-dimensional. A lot of this stuff can even be done in higher dimensions, though it becomes much harder to visualize what's going on in those cases. But a lot of these techniques do generalize very nicely, and we want to think about how we would go about computing these areas and volumes. But to begin this chapter, we want to motivate this definition of maybe a little bit of why we care about areas beyond their general applications. So example 1, we're asked which pair of numbers is closer together, a equals 4 and b equals 10, or a equals 100 and b equals 91. So something that we might do here is we might say, well, okay, I know how to take the distance between two numbers. You take the larger one minus the smaller one. So the distance between 4 and 10 would be 10 minus 4, which equals 6. And the distance between 91 and 100 is 100 minus 91, which is 9. So we see that 4 and 6 are closer together, or sorry, 4 and 10. So not the most exciting question, but maybe we want to generalize this, and we want to think, well, what does it mean to be the distance between two numbers a and b? So we're now kind of looking at the question here following example 1. And we might say, well, what we did there was we subtracted the numbers, so maybe let's write down this a minus b thing. But this isn't quite right. If we look at the previous example, if we were to talk about a minus b for a equals 4 and b equals 10, we'd be looking at the number negative 6. And it's kind of weird to say that a distance should be negative. By distance, we really mean something positive, or at least not negative. Maybe we should write that instead. Because two things can have distance 0 from each other, certainly if they're the same thing. So we want to look at a minus b, but we want to make sure that the answer is non-negative. And the way that we're going to do that is we're going to take the absolute value of a minus b. This guarantees that the result that we get is the same as if we had taken the larger one minus the smaller one. Right? If I take 4 minus 6 in this example 1 here, I get that I get minus 6 out, but then I take the absolute value of it to get something positive. If I had done the other example in the reverse order, so maybe I had done 91 minus 100, I would get minus 9, and I take the absolute value of it, and I get back to the plus 9 that I know the distance should be. So this kind of maybe gives us a little bit of an idea of how we would compute the distance between two numbers, but we want to generalize this question. A lot of what calculus is asking us to do is it's asking us to take these things that we know are true about numbers, talk about, equations and that sort of thing, and generalize those concepts to functions and talk about how do functions change. So if we have a notion of distance between numbers, maybe what we also want to think about is what does it mean for two functions to be close together? Can we describe something that might be a distance between functions? So let's explore this question a little bit intuitively at first, and we'll give maybe a more formal definition a little bit later. But if we want to think about the functions x squared plus 1 and 2x, and we want to ask the question, are they close together? Well, it's kind of difficult to do maybe without any numbers around. So maybe the first attempt that we have to answer this question would be just kind of plug in some numbers into these functions. So maybe let's look at something like f of 0 minus g of 0. But we know to talk about the distance between these numbers, we would want to take their absolute value. And so let's see, f of 0 is 1, g of 0 is 0. So we find that the distance between f and g, when we're looking at the x value 0, is 1. Well, that's maybe not enough information. Certainly there are other numbers that we might think about plugging in. So let's maybe try plugging in 1, f of 1 minus g of 1. If we plug 1 into the function f, we get out 2. And if we plug 1 into the function g, we also get out 2. So here we see that at the x value of 1, these functions have the same y value. So in fact, they're very close together. They're as close together as it's possible to be. Maybe let's think about plugging in another number. So let's try 100. If I plug 100 into f, I get 100 squared plus 1, which is 10,001. And if I plug 100 into g, I get 200. So doing this subtraction here, I'm going to get 8,001. Well, that's pretty far apart. So maybe what we're noticing here is that we're getting kind of conflicting answers. Because if we look at these two functions at the x value of 1 here, we get that they are very close together. They're as close together as it's possible to get. But if I look at these functions at the x value 100, I find that they're really far apart. They're 8,000 units apart. So plugging in numbers on their own isn't going to be enough to tell us how close together these functions are, because just plugging in numbers gives us some kind of conflict. It gives us some kind of contradiction. So instead, what we want to do is we want to maybe take a look at some pictures. Maybe try to figure out whether or not these functions are close together by graphing them. So let's see. So if I were to draw a graph of these functions, let's draw f of x in red here. So f of x is x squared plus 1, which we know is a upwards facing parabola, and it has y-intercept and vertex at the point 0, 1. We also have the function g of x equals 2x, which we know to be a line. It's a line with slope 2 and y-intercept 1. And these guys end up being tangent at some point. Not that you can exactly tell from my drawing, but they do intersect here at the point 1, 2, I believe we said. And so we have these two functions, and we can see, sure enough, yeah, they're close on kind of this interval, x values near 1. But as you move far to the right, or as you move maybe far to the left, then the y values get very far apart. So maybe this question itself isn't even well defined. What does it mean for two functions to be close together? Well, you should be asking, where are we looking? Are we looking at x values near 0, or x values near 1, or x values near 100? In that case, maybe we'll get different answers. But again, there's still kind of this ambiguity of distance depends on which x value you're at. So maybe let's take a look at some more pairs of graphs and see if we can develop some better intuition for how we might go about answering this question of what does it mean for two functions to be close together. All right, so example 2 is asking us again this very ambiguous question of the following pairs of functions, which are close and which are far. So if we look at this first pair of functions here, we see that, yeah, these are pretty close, whatever that means. The second pair of functions, these guys are pretty far apart, at least relative to our first pair of functions there. I mean, there's a lot of difference. Notice here that in both of these cases, the two functions have the same shape. So here we have red and blue have the same shape. where same shape means that kind of they each start by going up a little bit and then by going down, and they're sort of sinusoidal in that respect. Here we see the same thing. It's the same sort of shape, just kind of translated differently. So let's see, and we can make that same comment about this second example here. So let's see. So when we're talking about when two functions are close together, the right answer isn't going to be, do they have the same shape? Because we see here that functions with the same shape can be close together. Functions with the same shape can be very far apart. So we don't want to be looking at the shape of functions to determine whether or not they're close together. Let's see if we have a couple more ways to develop some intuition here. These functions maybe seem like they're not so far apart. We have some kind of distance here, and we have some kind of distance here, and some kind of distance here. But it seems that regularly they're at least getting close together. So maybe we could call these kind of far apart. Kind of far apart, kind of close together. And we could sort of say the same thing about these two functions. We have, they're maybe far apart there, but they're pretty close at x equals 4. So again, we get some kind of intermediate thing going on here. So maybe we want to look at the broader picture here and sort of decide what exactly is it that's making us say that these functions are close, these functions are far, and these functions are kind of somewhere in the middle. So maybe what I'll propose we look at here is we want to look at the difference between these two curves. And so if I were to draw the difference, so if I were to draw f of x minus g of x for each of these, I would be thinking about the difference in the y values. And geometrically, that can be represented by kind of these vertical lines that go between the various red and blue curves here. And likewise for this one, we have certainly consistently longer purple lines there. And if we look at these other guys, we have some more lines. And maybe what we would say is, this looks a lot like some pictures that we've been drawing already in this class. What we mean when we say that these functions are close together is that I've drawn very little area between the two curves here. And these functions are far apart because I've drawn lots of area between the two curves. And these functions are kind of far, kind of close, because I've drawn some kind of intermediate amount of area between them. Maybe something that's important to point out here is that if we were to think about this in terms of signed area, in the sense that some area counts for positive and some area counts for negative, we might say that these functions are closer together than we actually want them to be. Because we would say that this probably counts for positive area and this counts for negative area, and in the end these are going to cancel out and provide us with a much smaller estimate than we want to say. So instead what we want to ensure is that we're counting both areas as positive, or any area that we have between the two curves should count as positive. Because when we're counting it as positive, we're counting it as some kind of distance between the curves. We don't really care which function is larger or which function is smaller. We just want to count that as distance. And we want it to contribute in the same sense as telling us that about how far apart these functions are. So what we're going to do is we want to maybe make a definition about what it means to be the area between two curves. So if we're given integrable functions, f of x and g of x on the interval from a to b, the area between the curves is going to be the integral from a to b. This is our way of counting area. We want to talk about the area between the curves, so we want to look at kind of these purple lines here. And we said the way you can tell how tall a purple line is, well, you take the larger function minus the smaller function. And we saw this earlier. The way that you guarantee that you're taking the larger function minus the smaller function is you look at the absolute value of their difference. So in this case, the area between the curves is going to be the absolute value of f of x minus the absolute value, or minus g of x dx. One thing that I will point out here is that this is not the same as the integral from a to b of the absolute value of f of x minus the absolute value of g of x. So let's make sure to cross that out. This is not what it means to be the area between two curves, in particular because this integrand here could wind up being negative. This here will be a positive number, and this here will be a positive number. But if the absolute value of f of x is 5 and the absolute value of g of x is 7, then we get 5 minus 7 here, which is going to give us some kind of negative area. And that's the thing that we're trying to avoid here. So it's important to take f of x minus g of x and then take absolute values. In the next video, we'll actually take a look at some example computations.